Try this with me, eyes closed if you like. Take a box, an ordinary steel box, and pump out the air, every last molecule, until there is less inside than in the emptiest reach of outer space. Then cool the walls, colder and colder, down toward the coldest that anything can ever be, the temperature where all the ordinary jostling of heat is supposed to stop. Then wrap the whole thing so that no stray light, no radio whisper, no field from the world outside can leak in. By every instinct you have ever trusted, what is left inside that box is nothing. Perfect stillness, pure, empty space. And now, into that nothing, lower two small metal plates, plain, uncharged, facing each other like two pages of a closed book, and slide them close and closer until they nearly touch. And they get pushed together. Not by air, because there is no air. Not by magnetism, because there is no charge on them. They are pressed shut by the emptiness itself, as though the nothing between them were leaning on them. Something in that box is not nothing.
And I get a small chill every time, because the trap is to hear that as a poem, and it is not a poem. That push is a real force. You can hang a weight against it, you can measure it with a straight face in a laboratory, and people have. The empty space between those plates is doing mechanical work. So the sentence I want to earn tonight, slowly and honestly, is a strange one. Emptiness has a texture. The vacuum is not empty.
Okay, I want that, but I also have the annoyed undergraduate reflex already firing. The vacuum is not empty is exactly the kind of thing that shows up on a mystical poster next to a photo of a galaxy. So before you sell me anything, can we start from something I have actually done on a problem set? Something I could have derived myself?
That is precisely where I want to start. And here is the lovely part. You have already done the homework that gets you most of the way to that box. You did it the week you met the most over-assigned system in all of physics. Wait, this is just the harmonic oscillator. Let me ask you the question your quantum mechanics course asks. Right after the particle in a box, you solve the quantum harmonic oscillator, a mass on a spring done the quantum way. What is its lowest possible energy? The very bottom of the ladder.
The ground state. And the punchline everybody remembers is that it is not zero. The energies come out as a ladder. The bottom rung sits at 1/2 h bar omega, and each rung above it is one more h bar omega higher. So even in the lowest state, the oscillator has energy 1/2 h bar omega. It never sits perfectly still. And wait, is that where this is going? Is this whole thing just the harmonic oscillator, right?
That is exactly where this is going, and I could not have scripted your instinct better. Hold that thought like a coin in your fist, because we are going to spend it. But first, why not zero? A classical mass on a spring can absolutely sit dead still at the bottom of its well, with no energy at all. Why can't the quantum one?
Because of the uncertainty principle. If it sat perfectly still at the exact bottom, you would know two things at once with perfect precision. That it is right there at the center, so its position is nailed down, and that it is not moving, so its momentum is exactly zero, and you are not allowed to pin down position and momentum together. So the oscillator has to keep a little irreducible fuzz, a little jitter it can never switch off.
You just derived zero-point motion out loud, and you did it without a single line of algebra. That residual quiver in the ground state, that is the whole seed. Let me give you a picture for it, and then, because I promise to be an honest guide and not a hype man, let me immediately tell you where the picture breaks.
Please, break your own analogies before I have to.
Here is the picture. Think of the energy in the well as water. Classically, you can drain the well to the very bottom, bone dry, zero. Quantum mechanically, there is always a shallow puddle at the bottom that you can never bail out. That puddle is the 1/2 h bar omega.
And the limit of that picture.
The limit is the single most important thing in this whole episode, so I'm going to lean on it. The puddle is not water sitting on top of a lower, dry state you could reach if you were clever. It is the lowest state there is. There is no rung beneath it. Nothing below to fall into, nothing below to drain toward. When you hear the vacuum has energy, the sound of it makes you think of a fuel tank you could siphon. It is the exact opposite. It is the empty tank, the floor, the bottom of everything. Keep that, because it is going to save us from a very popular lie later.
Noted. And I already see the shape of the lie coming. But okay, I have one restless oscillator that can never hold still. That is a mass on a spring. How does one spring in a physics problem turn into an entire box of empty space pushing plates around?
One honest step. That is how. Watch. From one oscillator to a C. In your electromagnetism course, you learned that light is a wave in the electromagnetic field, and that you can break any electromagnetic wave into modes. Pure standing wave patterns, each with its own wavelength and its own direction, like the pure tones you can add up to build any sound. Now here is the one move that quantum field theory makes, and it is a move you can feel even without the machinery. Take each one of those modes and treat it as its own harmonic oscillator.
Each mode is a mass on a spring. The position of that spring is basically how strongly that particular wave pattern is ringing at the moment.
Exactly that. Each mode of the electromagnetic field is, mathematically, one more copy of the oscillator you already solved. And now spend the coin you have been holding. What did we just say every quantum oscillator has, even in its lowest state?
Oh, that is not fair. Every single mode has to have its own 1/2 h bar omega of jitter, even the lowest state, even when there is no light there at all.
Even when there is no light there at all. So the vacuum, genuinely empty space, no photons, no particles, the true ground state of the field, is not dead calm. It is the ground state of an enormous orchestra of oscillators, one for every mode, every wavelength, every direction, and every last one of them is humming its irreducible minimum. Not because anyone plucked them, but because the uncertainty principle will not let them be still, exactly the way it would not let your one mass on a spring be still. That is the seething sea. That is what is in the box.
So this is genuinely just the harmonic oscillator, copied a ridiculous number of times, once per mode and stacked up. I sort of resent how simple that step is.
You should. The whole art of this field is that the step really is that simple, and then keeping honest track of the consequences is monstrously hard. And here is a consequence you are about to ask about, so let me get ahead of it. People love to say the vacuum is a boiling sea of virtual particles popping in and out of existence. You have seen that sentence 100 times.
I was about to say it. That is the mental image I have. Little particles flickering on and off everywhere in empty space.
Then let me police that one hard, because it is the most misunderstood phrase in modern physics. Virtual particles are not tiny billiard balls that briefly wink into being and out again. They are a calculational device, bookkeeping terms in the mathematics of how fields interact, a way of organizing a very hard sum. You cannot catch one. You cannot put one in a detector. They never show up as real particles that leave a track. The cartoon of things popping in and out is a vivid picture for the restlessness, and it is fine as a feeling, but the moment you let it harden into there are real little objects there, briefly borrowing energy that we could grab, you have walked off the edge of the physics into fantasy. There is no borrowing. There is nothing to grab. Hold the jitter, drop the billiard balls.
Okay, so the honest version is every mode of the field has an unavoidable 1/2 h bar omega quiver, and virtual particles is a picture some people hang on the arithmetic, not a claim about tiny objects. Fine, but I still do not see how any of that pushes a plate. A quiver that is everywhere, the same everywhere, sounds like it should just cancel out and do nothing.
And that instinct is completely right, and it is the key that unlocks the box. If the sea were the same everywhere, you would never feel it. There would be nothing to compare against, and it would quietly cancel. So the whole trick, is to make it not the same everywhere. And two metal plates do exactly that.
This is the plates from the very top. Okay, how does a plate change the sea?
By being picky about which modes are allowed to exist between them. And you already know this physics from a completely different course. You know it from a guitar string.
A guitar string, because a string clamped at both ends can only vibrate at certain wavelengths, the ones that fit with the ends held still. A whole number of humps. You cannot play a note in between, it just is not available on that string.
Precisely. Now slide two conducting plates close together, facing each other. A conducting plate forces the electromagnetic field to behave a certain way right at its surface, pinned like the clamped end of the string. So between the plates, only certain wavelengths fit. Only the modes that close up neatly in that gap are allowed. Every other wavelength, and there are vastly more of them, is simply not permitted to exist in there. But outside the plates, in the open room, the full, unrestricted set of modes is present. Every wavelength, no exclusions.
So the gap between the plates has fewer available modes than the open space outside it. Fewer oscillators humming their half h-bar omega in there than out here.
Fewer inside than outside. And now, before you run ahead, let me label the guitar string picture, because it is an analogy, and analogies have edges. It is not literally sound, and the plates are not literally the nut and bridge of a guitar. It is the electromagnetic field's own standing wave patterns being restricted by the conducting boundaries. And here is the edge that actually matters physically. Real metal plates are not perfect mirrors at every wavelength. Crank the frequency high enough, very short wavelengths, and the metal simply goes transparent. The field sails straight through as if the plates were not there. Which is a good thing, because it means the plates only really exclude modes in a limited band, and the whole effect comes out finite and measurable instead of infinite. Tuck that away. It is the entire reason this is physics and not a paradox.
Got it. The plates are picky only over a band because they leak at high frequency. So, fewer modes humming inside the gap, the full set humming outside. And I think I can finish this myself. Fewer humming modes means less of that 0-point restlessness pushing outward from inside the gap. But the outside is pushing inward with the full set. So there is more push from outside than from inside, and the plates get shoved together.
You just built the Casimir effect with your own hands. That is it. That is the entire mechanism. The plates are squeezed together not by something that is there, but by something that is missing. By the modes that the gap is too narrow to hold. Empty space pushes them shut because the emptiness between them is, in a very precise sense, a little emptier than the emptiness outside.
That is genuinely one of the strangest true sentences I have ever heard. Give me another analogy because I want to make sure I have the geometry and not just the words.
Here is the sailor's one, and it is real folklore. Two ships sitting close together, side by side on a choppy sea, can get pushed toward each other. Between the hulls, the water is relatively sheltered. The biggest waves cannot fit in that narrow channel, while outside, the full ocean is heaving against them. More wave pressure from outside than from the calm slot between, so the sea nudges the ships together.
And the limit on that one?
Good. Always ask. The limit is that there is no water in our story. No medium, no fluid, nothing sloshing. The ships and waves picture captures the geometry of the imbalance and nothing else. Full field outside, restricted field in the gap, net push inward. But what is imbalanced is the zero-point structure of the quantum field itself, not a sea of actual stuff. Take the shape of the argument, leave the ocean behind.
The shape without the ocean. And how strong is this push really? Because so far it sounds like the kind of thing that is true but a trillion times too weak to ever matter.
It is ferociously sensitive to how close the plates are. The force per unit area climbs as 1 over the separation to the 4th power. So halving the gap does not double the push, it multiplies it by 16. At the width of a human hair, it is nothing, utterly negligible. But bring the plates in to about 10 nanometers apart, a stack of maybe a few dozen atoms, and the pressure squeezing them together climbs to roughly 1 atmosphere. The same push the entire weight of the sky puts on your shoulders right now, produced by nothing but the modes that cannot fit in the gap.
1 atmosphere, out of the missing part of empty space. Okay, who thought of this, and how do you ever measure a force that only wakes up when 2 plates are a few dozen atoms apart? A force from nothing.
The idea came first, and it came from a man named Casimir, working at the Philips Research Labs in the Netherlands in 1948. He worked out that 2 uncharged, perfectly conducting plates in a vacuum should feel exactly this attraction. A pull with no charges and no fields to explain it, arising purely from the shift in the zero-point energy of the electromagnetic field when you slide the plates in and change which modes are allowed. That same year, with his colleague Dirk Polder, he worked out the cousin of the effect, the force between a single atom and a surface. His name has been on it ever since.
So the plates snapping together release a little energy. They fall toward each other, so they do work, so energy comes out. And now I have to ask the question that mystical Poster wants me to ask. If empty space pushes the plates together and that releases energy, is this free energy? Have we found a way to power the world from the vacuum?
No. Flatly, warmly, no. And I am glad you asked it straight out, because this exact topic is a magnet for that scam, and I want to disarm it cleanly. Go back to the puddle at the bottom of the well that we said we would spend. The zero-point energy is the energy of the ground state, the lowest state there is. There is nothing beneath it. You cannot extract net usable energy from a system that is already sitting on its own floor, because there is no lower place for it to fall to.
But the plates do snap together and release energy. I did not imagine that.
You did not, and here is the honest accounting. When the plates snap shut, yes, they release a small burst of energy, once, but now you are stuck. The plates are together. To run this again, you have to pull them back apart, and pulling them apart against that same attraction costs you at least as much energy as you got out, and in practice more. There is no cycle. You get one payment and then you are underwater forever. It is exactly like letting 2 magnets snap together and calling it free energy. The snap is real, but you have to spend to reset it. So when you see a product called a zero-point energy generator or a vacuum energy device, you are looking at a scam, full stop. Not a promising frontier we have not cracked yet. A physical impossibility dressed up in real vocabulary. The vacuum is the ground state by definition. You cannot mine the floor.
That is the clearest version of that I have heard, and I appreciate that you did not hedge it. Okay, so the effect is real but not a power plant. Back to the lab. How did anyone catch a force this shy?
The first real attempt came a decade after the prediction, in 1958. A physicist named Marcus Sparnay, also at Philips, tried it with flat metal plates on a spring balance. And here is the honest scorecard. His result was consistent with Casimir's theory, but the error bars were enormous. The most he could truthfully say was that his measurement did not contradict the prediction. That is not a confirmation. That is a shrug in the right direction. The hard part is brutal. To use 2 flat plates you have to hold them perfectly parallel while a few atoms apart, and the tiniest tilt wrecks it.
So how did they beat the parallel problem?
They cheated the geometry beautifully. In 1997, Steve Lamoureux, then at the University of Washington, did the measurement that reopened the whole field. Instead of two flat plates, he used a flat plate and a gold-coated sphere. A sphere and a plate do not need to be aligned. A sphere looks the same from every angle, so there is no parallelism to get wrong. He hung it all from a torsion pendulum, an exquisitely sensitive twisting balance, and measured the tiny attraction as he varied the gap. He found agreement with Casimir's prediction at about the 5% level. That was the experiment that convinced people this was a real, quantitative, measurable force, and not just a textbook curiosity.
5%. That is a real measurement, not a shrug, and I bet someone immediately did better.
The very next year, 1998, Umar Mohideen and Anushree Roy at the University of California, Riverside, pushed it to high precision using an atomic force microscope, the same kind of instrument that feels its way across individual atoms on a surface. They mounted a tiny metallized sphere on the microscope's cantilever and measured the force across separations from about 100 nanometers out to 900, and at the closest approach, they matched theory at roughly the 1% level. That is the first genuinely precise confirmation. After that, the Casimir force is simply a fact, as measured as the charge on the electron.
So can I now say the thing the poster wants to say? The Casimir effect proves the vacuum is full of zero-point energy. It is measured. It is 1%. We are done.
And here is where I have to slow you down, because this is the subtle one, and being honest about it is the whole reason a show like this is worth doing. The force is absolutely real and absolutely measured. Nobody argues about that. What is genuinely debated is what it proves. There is a well-known argument. The sharpest version is due to a physicist named Robert Jaffe, around 2005, showing that you can compute the entire Casimir force without ever mentioning the zero-point energy of empty space at all. You can derive it instead as a relativistic version of the ordinary force between the charges and currents living inside the two metal plates, a cousin of the van der Waals force that makes ordinary molecules stick. And the tell is this: in that derivation, the force smoothly vanishes if you imagine turning the electric charge of the plate's electrons down toward zero. If it were purely a property of empty space, why would it care about the charge in the plates?
So the Casimir force is consistent with the picture of a zero-point C, but it does not uniquely prove that the C is a real, freestanding tank of energy sitting in empty space. It could just be a force between the plates, dressed in vacuum language.
That is the honest sentence, and I want you to carry it exactly that carefully. A real, measured force, whose most popular and most intuitive picture is the restless vacuum, but one that can also be derived as a quantum force between the plates, with no vacuum reservoir invoked. Real force, contested interpretation. Anyone who tells you the Casimir effect settles what the vacuum is skipping past a live debate.
I like that you fenced it instead of selling it. Is there any other place the vacuum reaches out and touches something we can measure, something that is not two plates?
There is, and it is older than Casimir's plates, and it happens inside every atom. It is called the Lamb shift. The vacuum jiggles an atom. In 1947, Willis Lamb and his student, Robert Rutherford, at Columbia University, were doing exquisitely careful spectroscopy on hydrogen, the simplest atom there is, one proton and one electron. And they found something that should not have been there. There are two particular energy levels in hydrogen. Physicists label them the 2s level and the 2p level, that the best theory of the day, Dirac's equation, predicted should sit at exactly the same energy. Identical. Degenerate in the jargon. And Lamb measured them and found the 2s level sits very slightly above the 2p, a tiny gap that, by the reigning theory, had no business existing at all.
How tiny?
Tiny, a splitting of roughly 1,000 megahertz if you measure it as a frequency, a whisper of an energy difference. But its size was not the point. The point was that it was not zero, and Dirac said it must be zero. So where did it come from? And a good part of the answer, this is why it belongs in tonight's story, is the vacuum. The electron in the atom is not orbiting in genuinely dead space. It is sitting in that seething sea of zero-point field we have been describing, and that fluctuating field jiggles the electron, smears its orbit out just slightly, and nudges its energy. The two levels respond to that jiggle a little differently, and the degeneracy breaks. The vacuum, in other words, reaches into the atom and moves an energy level by a measurable amount.
So the Lamb shift is the vacuum leaving a fingerprint on the hydrogen atom, and I take it this mattered a lot, historically.
It lit the fuse. That little splitting was one of the central puzzles that forced physicists to build quantum electrodynamics, the full quantum theory of light and matter, and to invent the whole apparatus of renormalization to handle exactly these vacuum effects without drowning in infinities. It was that important, and Willis Lamb won the Nobel Prize in Physics in 1955 for it, sharing that year's prize with Polycarp Cush, who had measured a related vacuum fingerprint on the electron's own magnetism.
So we have the vacuum pushing plates and the vacuum shifting atomic levels. Is there anything even wilder? Can you ever get the vacuum to hand you something you can actually catch, like a real particle?
You can. And it is the most cinematic result in this whole story. You can make a mirror pull real light out of empty darkness, real light out of the dark. Here is the idea, and it goes back to a prediction by a physicist named Gerald Moore in 1970. Take a mirror and move it, but move it fast, at a serious fraction of the speed of light. When a mirror moves that violently through the vacuum, it cannot smoothly rearrange the zero-point field around it. It disturbs the sea so hard that some of that restless field energy gets converted into real, honest photons. Actual light, in an actual detector, born out of what looked like empty darkness. It even has a name that tells you it is the moving cousin of the plates, the dynamical Casimir effect.
A mirror moving at a fraction of light speed. That is absurd. You cannot shake a real mirror that fast. It would tear itself apart long before.
You cannot. And that is exactly why it sat as a prediction, untouched, for about 40 years. Nobody could move a mirror anywhere near fast enough. The breakthrough, in 2011, was to stop trying to move a real mirror at all. A team LED by Christopher Wilson at Chalmers University of Technology in Sweden built an electrical mirror instead. They used a superconducting circuit element called a squid to change the effective length of a waveguide back and forth extremely fast. They were not sloshing a physical slab of glass, they were sloshing the boundary that the electromagnetic field sees, and they could make that boundary effectively move at a few % of the speed of light. Fast enough. And out came photons, real microwave photons, measured, conjured from the vacuum, matching the prediction.
So they did not move a mirror near light speed. They moved what the field thinks is a mirror, and light came out of the dark. Is that a fair way to say it, or am I overselling?
That is a fair way to say it, with one honesty flag I want to plant. It is not free energy. I know your reflex by now, and no, it is not, because it takes real energy to drive that circuit fast, and that energy is where the photons come from. You are converting the drive energy, not mining the vacuum. But the genuinely astonishing part stands. The specific photons that come out carry the fingerprint of the vacuum fluctuations themselves. The apparatus turns the restlessness of empty space into countable light. It was named one of the standout physics results of its year, and rightly.
Okay, plates pushed by missing modes. atomic levels nudged, light pulled out of the dark. This is the part of the episode where you have been good all night about where the bridges end, so give me the honest edge. Where does the vacuum stop being a triumph and start being an embarrassment?
Right now. And it is not a small embarrassment. It might be the single worst quantitative prediction in the history of physics. The worst prediction in physics. Here is the reasoning, and every step of it is one you can follow. We have said the vacuum is the ground state of an enormous orchestra of oscillators, each humming its half h-bar omega. That energy is real enough to push plates and shift atoms. So let us do the obvious thing, add it all up. Sum the zero-point energy of every mode of every quantum field, and you get a total energy density for empty space, a certain number of joules of vacuum energy in every cubic meter of nothing.
And here comes general relativity, I bet. Because in general relativity, energy is not a bystander. Energy gravitates. Anything with energy bends space-time.
You see exactly where this goes. In Einstein's theory, that vacuum energy density cannot just sit there being ignored. It gravitates. It acts like what cosmologists call a cosmological constant, a uniform energy filling all of space, pushing on the expansion of the universe itself. So we can ask a sharp quantitative question. Take the vacuum energy that our best theory of the very small predicts, feed it into our best theory of the very large, and ask how much it should be bending the whole universe. And then we can go outside and measure how much the universe is actually being bent.
And we can measure that. We know the real answer to compare against.
We do, and that is the beautiful, maddening part. In 1998, two teams, LED by Saul Perlmutter and by Brian Schmidt and Adam Rees, discovered that the expansion of the universe is not slowing down, as everyone expected, but speeding up. Something is pushing space apart, gently, everywhere. That something behaves exactly like a small cosmological constant, a real non-zero vacuum energy, and it is now called dark energy. That discovery earned the Nobel Prize in Physics in 2011. So the universe hands us a genuine, measured value for the vacuum energy. It is small, but it is really there.
So we have a prediction from adding up the zero-point modes, and we have a measurement from the accelerating universe. Two numbers for the same thing. How badly do they miss?
Prepare yourself, and let me be careful about how I say it, because the honest version is a range, not a single sacred number. The naive theoretical prediction overshoots the measured value by somewhere between 50 and 120 orders of magnitude.
Orders of magnitude. So we are not talking about being off by a factor of a few, or even a few thousand. Between 50 and 120 orders of magnitude is, I do not even have a word. 120 orders of magnitude is a 1 with 120 zeros after it.
There is no word, and there is no analogy that survives it. Every comparison people reach for, grains of sand, atoms in the universe, falls hopelessly short of 120 orders of magnitude. It is not a discrepancy, it is a chasm. Our best theory of the vacuum and our best theory of gravity, brought together, produce the worst mismatch between theory and experiment anywhere in science. It has a name, the cosmological constant problem, and it is exactly as unsolved as it sounds.
Wait, you gave me a range, 50 to 120. Why a range? Shouldn't the theory just give one number?
That is a sharp question, and it goes to why this is genuinely hard. So let me be honest about it. The answer depends on where you stop adding. Remember, we said real plates go transparent at very high frequency. The sum over modes has to be cut off somewhere. If you trust the theory all the way up to the highest energy scale we think is meaningful, the Planck scale, you get the full monstrous overshoot, around 120 orders. If you only trust it up to lower, better tested energies, The overshoot is only 50 or so orders. Either way, it is catastrophic, but the exact figure depends on that choice, which is why an honest person quotes it as a range and not one number. Anyone who gives you a single triumphant figure is pretending we understand this better than we do.
So this is not a near miss that a clever correction will tidy up. This is our two best theories flatly disagreeing by an amount that has no name.
That is the state of it, and I want to resist every urge to hand you a bow. People have proposed fixes, deep symmetries that might cancel the vacuum energy, selection arguments about why we happen to live in a universe with a small one, all sorts of ideas. None of them is accepted. None of them is established. This is not a solved problem that I'm simplifying for a public audience. It is an open cliff, and everyone standing at the edge of it knows it. Our framework for the small says the vacuum should wreck the universe. The universe is manifestly not wrecked, and nobody knows why.
Let me try to say the whole thing back to you honestly, the way you have been modelling all night. Proved, then believed, then genuinely unknown. We have proved the harmonic oscillator's ground state is 1/2 h bar omega, not 0. That is just first-year quantum mechanics. We have proved that empty space pushes two close plates together. The Casimir force, measured to about 1% by Lamoureux and by Mohideen and Roy. We have proved the vacuum shifts an atom's energy levels. The Lamb shift, Nobel-honoured. We have proved you can pull real photons out of the dark with a fast enough mirror, the dynamical Casimir effect, 2011. All of that is just true.
All of it, flatly. Keep going.
But we have not proved what the vacuum fundamentally is, whether it literally contains a sea of energy, or whether that is a vivid picture for mathematics that can also be written as forces between charges. That is genuinely contested, and we have not the faintest idea why the vacuum energy the universe actually carries is smaller than our theory demands by 50 to 120 orders of magnitude. That is not believed but unproven. That is flat out unknown.
A flawless summary, and holding those three things in three separate hands, the proved and the contested and the unknown, is the entire discipline of doing this honestly. So here is what I want you to walk out with. Every measured thing in this episode was, not long ago, thought to be untouchable. A philosopher's daydream about whether empty space is really empty. And then people your age, sitting where you are sitting, turned it into torsion balances and atomic force microscopes and superconducting circuits, and they measured it. The daydream became a lab, and the cosmological constant problem, the chasm at the end, that is not a closed door. It is the biggest open question we have, sitting right at the seam between the physics of the very small that you are learning this term and the physics of the very large. It is waiting.
And it started from the harmonic oscillator, from the one problem I was sure I already understood.
From the one problem you were sure you already understood. Its ground state is not 0. You knew that on a problem set. Copy that one fact once per mode of every field, and you get a vacuum with a texture, a force out of nothing, light out of the dark, and a crack in physics 120 orders of magnitude wide. That is the whole trip, and it is one honest step past this week's homework.
One honest step past the homework. I came in ready to roll my eyes at the vacuum is not empty, and I am leaving unable to unsee it. Thank you, genuinely.
Go find the recording of the Chalmers result, or a plot of the Casimir force, and sit with the fact that empty space did that. Then go do your next problem set, knowing the floor of the world is humming, and that nobody yet knows why it hums so quietly. That is not a gap to be embarrassed by. That is the door.
Then that is where we will leave it. At the door, not the bow. Until next time, the vacuum is not empty and the emptiest question in physics is still wide open.